So my name is Jorge Meneses. I am the current third Kenji Ishihara Colloquium Series on earthquake engineering. So first, to start this session, we are going to show a video message sent by Professor Kenji Ishihara, who asked me to convey this message to all of you. It's 4 in the morning in Tokyo, Japan, so it's too early for him to send this message directly.
Good morning, everybody. Ladies and gentlemen, Chairman Dr. Jorge Meneses, a good friend of mine, I am very pleased to learn that the third colloquium in its series is now to be held in San Diego. Even in the difficult time now, I learned that the subject title this time is Soil Structure Interaction. One of the important issues associated with the subject would be firstly, the behavior of foundation piles as influenced by soil liquefaction in the surrounding ground. Secondly, the stability or movement of the key walls in port and harbor areas will be another important subject to be discussed in details. Another subject I can think of would be the differential settlement of the private houses and buildings sitting in or under the ground where liquefaction developed. The another subject area would be floating up of lifeline pipes near the surface, such as sewage lines and so on. These have been observed many times in the past during the recent earthquakes. I think these will be discussed thoroughly during the colloquium. One of the devastating recent event, liquefaction-induced landslide, which occurred in Indonesia, Sulawesi Island. I learned that more than 2,000 people were killed, involved in the huge landslide, which have a diameter, width of 1 kilometer and length is almost 2 kilometers. This is the first time I heard people were killed due to liquefaction. As a matter of fact, at the time of Niigata earthquake, nobody was killed. So in that sense, the events in Indonesia is the unprecedented events, and everybody should pay attention seriously to the cause and countermeasures of such big disasters. There are several persons in Japan, such as Professor Kokosho, Yasuda, Tohata, and Kyoto, who went there and investigated the details of these studies. But I don't know whether they are making presentation in this third colloquium. They will probably make a more extensive presentation in the next one. I personally visited twice there, and I was very much shocked or surprised why such a disaster have taken place. One of the reasons I can think of is the existence of aquifer pressures, underground high water pressures coming from three causes. The one is the leakage of the irrigation water from the nearby canal during the last 20 years. The second causes appears to be the groundwater table coming from the nearby mountains as a underground water. The third conceivable cause of the underground water is the upward movement of the earthquake-induced volcano waters, which came up through several fissures caused by the earthquakes. So these are the conceivable reasons, but no evidence is clearly defined yet. So this would be clarified, I hope, in the future, but it will be very difficult. Anyhow, I wish all the participants of the colloquium will enjoy the meetings, and we will see each other again, probably next years, under the help of Dr. Jorge Menezes, who has been working very hard to organize this conference. I really appreciate the willingness or incentives of Jorge Menezes to organize such a useful colloquium. Thank you very much.
Thank you very much, Professor Ishihara. So next, we are going to have Ms. Tasneem Sadiq, our Director of Communications, member of the Regional Board of EERI San Diego, and she will make some announcements.
Great. Thank you, Dr. Menezes, and thank you everyone again for being here. Today is the last of our colloquium series this year, following up on the 2 previous webinars we've had so far this month. The first being on base isolation 2 weeks ago, moderated by Gilberto Mosqueda. And the second being on damping systems last week, moderated by Alvaro Celestino. And today is the third and final part on soil structure interaction, which will be moderated by Jorge Menezes. And of course, a big thank you to our sponsors for helping to make this year's colloquium possible. They are the Seismic Safety Commission, California Geological Survey, Maurer and Keller as our silver sponsors, and RMA companies, Degenkolb Engineers and Tensar as our gold sponsors. And in addition to our sponsors, you all, especially the members, help make EERI who we are. If you are currently a member of EERI, thank you so much for your membership. We are very glad to have you and appreciate your support. And if you're not yet a member, please consider joining us. Head on over to our website and click the Join Us tab on our main page, or you can use the direct link shown here. Now, as a reminder, you'll be able to access this presentation after it's over, so you can review these links and slides again later. As a member, you'll enjoy many benefits, such as attending our events and meetings at a discounted price or for free, and getting the opportunity to network with esteemed professionals and educators across various engineering fields. To become a regional member is only a modest fee of $25. And next up, we have some events coming up after our colloquium, all of which are going to be in Pacific time. Now, the first event that we were asked to share about is a training that will be aimed at structural engineers about the seismic evaluation of older concrete buildings for collapse potential. This event is hosted by Cal OES, funded by FEMA, and organized by ATC. This is a free training that will be on Wednesday, June 9th from 9 a.m. to 1 p.m. and you can register at the link shown here. Then on Friday, June 11th, 2 days later, from noon to 1:30 p.m., we have Dr. Kevin W. Franke of BYU presenting a webinar on the topic shown here. This is the registration link, which can also be accessed by visiting our chapter website. Register to reserve your spot. This event is free. And lastly, Professor Enrique Luco is a distinguished faculty emeritus who recently retired from UCSD. And we are considering organizing this event to honor his contributions to soil structure interaction and earthquake engineering. So be on the lookout in the later part of this year for an announcement on this. That just about does it for our upcoming events and our announcements. Now back to our moderator to introduce our speakers for this afternoon.
Thank you very much, Tasnim. So before starting the presentations, just a reminder that all questions should be asked in the Q&A section. We will be monitoring this throughout the sessions, and we'll try to get to as many as we can in the questions and answer portion of the webinar. So this is after the 3 presentations that will be presented in a row. Any comments, technical issues, etc., can be put in the chat. So our first panelist is Bret Lizundia. He's an executive principal with Rutherford+Chekene. He's a structural engineer in San Francisco. He has over 30 years of experience in structural design of new buildings, seismic evaluation and rehabilitation of existing buildings, peer review and plan checking, and applied research and guideline development. He was a project manager and co-author of FEMA 547, Techniques for Seismic Rehabilitation of Existing Buildings, a co-author of FEMA 306-307, Evaluation of Earthquake Damage, Concrete and Masonry Wall Buildings, Project Technical Director for the update to FEMA P154, Rapid Visual Screening of Building for Potential Seismic Hazards, Project Technical Director for FEMA P-2006, Example Application Guide for ASCE SEI 41-13, Seismic Evaluation and Retrofit of Existing Buildings, and Project Technical Director for FEMA P-2091, a practical guide to soil structure interaction. He's a past president of the Applied Technology Council and the Structural Engineers Association of Northern California. Bret, the floor is all yours.
Great, thank you very much. All right, well, I'm pleased to be here. I'm joining you from what is currently sunny Northern California rather than San Diego through the webinar. And the subject today, which will kind of introduce the topic in general of today's session, is a document that was issued at the end of 2020 to help practicing engineers implement and better understand soil structure interaction. So I'm going to be discussing first kind of the lingo that we use in SSI, some of the basic ways it's modeled, and then cover what's in that design guide to help. Some of the things that will be included is when is SSI important? When is it going to make a difference in the way the building behaves? A rule of thumb test that was developed to help easily determine when inertial SSI effects are helpful. There's a handful of topics in ASC 7, which governs structural design of buildings in America. And so I'll be covering each of those because we included those in the design guide. A a common topic that we included in the guide that happens, you know, to engineers all the time is what to do when you have a basement. What are the kind of best ways and easiest ways to do that? We have some very detailed examples for a couple of different kinds of buildings in the design guide. So I'll give you a taste of what's included in that. And then I'll wrap up with a discussion of kind of some tips and some advice from what we have learned over time that hopefully are things you can take away. So my goals are to give you at the end, and I know we probably have a mixed group of people with lots of experience in this and probably others with less experience. And so for those of you with less experience, I'm hoping you'll come away with a better understanding of the different ways that you can do soil structure interaction modeling. You'll have a better feel for the, you know, slightly cryptic and obscure terms if you're not used to using them and what they mean. Also, get a feel for when SSI may likely matter in the buildings you're working on and when it may not. There's plenty of buildings where it doesn't make a significant difference and it's not a good use of fee or time to be including that sophistication. And then an understanding of some of the key resources that have been developed in recent times to help engineers implement this. So let me start first with some terminology. You know, every discipline has its lingo, and this is one, you know, set of terms that's been developed and I think has sort of a general consensus in the community. So we'll start with this building on the left that's embedded one story into the ground, and that UG there on the right, that's the denoting the free field motion that comes up through the, you know, source and eventually reaches the site and would be there, what would be experienced if the building didn't exist. You know, on the way it's getting there, that's what it is. And then it's going to change as it gets closer to the building. So there's kind of two basic categories of effects that are part of SSI. One is called kinematic effects and the other is called inertial. So kinematic interaction changes that free field motion, and what the building at the bottom of it feels is that foundation input motion, which is not the same thing. Inertial effects are a little bit like the inertial loads that we are used to in the superstructure. So the mass of the building being accelerated and generating forces that the members have to resist. A similar thing happens with the soil that's near the building and the foundation itself, and there's a combined soil structure effect that includes those inertial issues. So that's sort of the biggest, broadest, highest level ideas. Let's drill down into that a little bit though. So if we talk about the kinematic SSI side, so, you know, one definition of that is the modification of that free field ground motion into the foundation input. And that's a result of spatial variability. So the motions that are experienced at one corner of the building footprint and another corner are not the same. And one effect called base slab averaging is where there's a combination and a kind of overlap and thus an averaging of those waves that the building eventually feels. So it's experiencing all these inputs, but it has to eventually kind of smooth them out. And that tends to reduce the effect of the worst one. Somewhat similarly, the embedment. So smaller embedments change the motion less. Deeper embedments have a bigger effect, which has sort of been shown through past measurements and experience and analysis as well. So on the inertial side, three effects are commonly identified. So one is that if we account for the softness and flexibility of the soil and its ability to augment the movement of the superstructure. So the building can tilt more than it would if you just fixed it unrealistically hard to the ground. Then that will increase the building period. So that period lengthening can affect the way response spectral forces are experienced in the building. And they can go up and they can go down. They typically go down, and we'll talk about that in a little more detail. Two other effects, less commonly implemented or even discussed really by structural engineers, are two forms of damping. So one is called radiation damping, where that damping in that soil structure system of the combination of the foundation and the nearby soil, that damping is caused by the generation propagation of waves away from the foundation, which are in turn, caused by different dynamic displacements of the foundation relative to the free field displacement. So the ground and the building are in contact and moving, but not necessarily moving identically. Soil damping is a little bit of a simpler phenomenon. And it's similar or analogous to the way we think of inherent viscous damping in the superstructure. So, we usually 5% is sort of a classic number that we use up in the superstructure to represent all the non-structural components that are going to be cracking and absorbing energy. There's a similar kind of effect in the ground. So our design guide that we put together tackled all those topics that I showed you. There's a chapter on there's a chapter on base live averaging. There's a chapter on period lengthening. We discuss basements. We talk about this rule of thumb that I'll show you in a minute. And we're focusing on techniques that practicing engineers can use. So this is less sophisticated treatise on finite element nonlinear modeling and more a discussion about the wonders of springs and when to use them and how to do that. So here's some pictures that were originally, the picture on the left was in a seminal publication that one of our speakers today, John Stewart, was in charge of. And this is showing that finite element version. So sophisticated infrastructure projects, a nuclear power plant, a buried, liquid gas tank, some, important underground subway, might be done this way, where the soil elements in a big model are also finite elements. The vicinity around the boundary around the structure is done a little differently, but it's similar kind of elements, and then the structure itself is part of that. So this is computationally intensive and requires a lot of skill and knowledge and usually special software to be able to do. That is not what typically happens in the structural engineering community for buildings. What we're used to using as a building engineer are a much simpler, what's called a substructure approach rather than a direct analysis approach, where we're putting vertical and sometimes horizontal springs underneath the bottom of the building to represent the soil and sometimes the foundation flexibility. And that's the focus of this design guide and the focus of what I'm going to be talking about today. So the purpose, to kind of repeat a little bit of what we're trying to do, we're trying to help practicing engineers. So this is not an academic document. This is really targeted for people who are designing buildings, primarily structural engineers, although geotechnical engineers would certainly benefit from this. And we want to help them know when soil structure interaction is important, and we want to show them worked examples of how to implement different techniques. So I have lots of pictures, usually fairly simple examples. Here's an example of embedment. So there is a rule in ASC 7 about how you define the bottom. So if you had a partial basement here, you have different depths of embedment. You count only the depth that is greater than 75% of the footprint of the building. So in this case, it's a little more than half. It's less than that 75%. So from the code point of view, the depth of embedment is actually the shallower side in this rather than deepened side. So that, codes are conservative, and this is the way that they've approached it. So we have lots of pictures like this of different examples to help people understand what are sometimes kind of cryptic provisions in the building code. And that target audience, then, it's obviously engineers, kind of two kinds of engineers. So our primary audience is practicing engineers who definitely are familiar with seismic design. They've designed buildings, but they may not have ever implemented or used SSI. They may have just fixed the bottom of their buildings, been doing a great job, understand the building code very well, but are now interested or facing a need to deal with SSI, and this is something they can turn to. The secondary audience is people with a little more experience who may have done some soil structure interaction work, often with vertical springs on a past project, but now they want to try or they see a need to go farther than that and tackle sort of other areas of SSI. So we had a great group of folks. Two of our other speakers were both on this project. So John Stewart was part of the author group of people on the technical committee. And then Sissy was one of our reviewers. This was all a FEMA funded project. So Mike Mahoney was the lead project officer, and FEMA usually engages another direct reviewer. They call it a subject matter expert. So very experienced, engineer and professor Bob Hansen was that reviewer. This was run through the Applied Technology Council as one of their many projects, and Aisha was our excellent project manager. We also had a number of people doing kind of specific tasks on different subtle issues. So you can see those working group members on the right. So I'm indebted to all of these great people who helped bring that project to completion. This follows on another, I would say, really seminal document that I mentioned earlier. It was called ATC 83, but this was NIST funded instead of FEMA funded. So this helps form the underlying basis of the current provisions that are in ASC 7 for new buildings and ASC 41 for existing buildings. And one of the things that John was trying to do in creating this that I think was really important is that he was trying to create not just a comprehensive compilation, but a consistent set of terminology, and to organize and present equations that had been done in different ways by different researchers over the years, but put them all together in a way that was consistent. There were a lot of aspects to this. Besides that, we had some significant case study examples. It was pretty sophisticated, and you still, to use this, you would usually, be relying on a very knowledgeable geotechnical engineer who would take advantage of this. So it wasn't intended, nor is it really that easy to use for your average sort of structural engineer like myself. So this slide, I wanted to give you a feel for kind of the world of other resources that have happened and kind of the progression over time, because it's not just, the two documents I mentioned so far. There's a whole lot of work. So early SSI, has been around for a long time. Lots of papers and analyses and work was done by some seminal researchers in the field. But from the kind of everyday building side of the world, it was relatively, little used. It was perceived as, kind of challenging, difficult, a lot of really long equations that you needed to be fairly experienced to understand. So it rarely implemented in everyday practice. And then there was a group of documents, FEMA and ATC documents that you can see over there, where this began to be included in a more sort of practical way with provisions. Then this seminal work that John was in charge of came out, and the newer updates to ASC 41 and ASC 7 included that. There was a design guide, the FEMA P1051 design guide, which provides worked examples for how to design buildings, for seismic issues in general, included some discussion of soil structure interaction. FEMA-P 2006 is the design guide for ASC 41, 13, and 17, and it has some significant discussion and worked examples for SSI and just foundation issues in general in it. And the peer TBI documents used for tall buildings also has some discussion of SSI issues. So we are getting closer and closer to, what I'll call the end zone, getting closer to the red zone, and then ultimately the end zone of being able to deliver kind of a practical success to practicing engineers and giving them examples that they could realistically use. And so our P 2091 guide here, we hope does that, but there's already more work en route. So the next editions of ASC 41 and ASC 7 are going to have some updates to all of this based on the lessons learned and some tweaks as we move the profession forward. So here's an outline of the guide, and you can see all the chapters that are listed there. I'm going to be covering a number of these in the minutes ahead of us. There's a chapter on each of the effects in ASC 7. There's also some additional work, and then there's these very significant appendices that are worked examples on the building scale. So usually in the earlier chapters, they're sort of smaller, focused examples on a topic, whereas the appendix A and B examples are broader, kind of full building analyses. So let me kind of go over one of those earlier chapters to kind of give you a feel and hopefully some takeaways, particularly for those of you where this is somewhat new. When is SSI going to be likely to be important? So some of these are pretty simple, and I've already mentioned them to some degree. A building with a larger footprint will tend to have some greater reduction in the foundation input motion than the smaller one. So the building on the left, we're going to be able to reduce the forces a little bit more than the building on the right. And that is primarily due to the kinematic interaction effect of base slab averaging. The bigger your base, the more you average, the greater the reduction. Somewhat similarly, the other kinematic effect of foundation embedment tends to reduce that. So the building on the left, if it had the exact same footprint, but has 2 stories of basement embedment, will tend to have lower forces. Both of these effects tend to be a short period focused issue. The reduction in the long period range is usually negligible, but the reduction in the short period range, and these are short period buildings on the screen, is where it matters, where this kicks in. So now on the kind of inertial SSI side, if we have a high structure to soil stiffness, so a way to think of that is if the building is stiff, so to speak, a shear wall building, and the ground is soft, then we tend to have more rocking. So if we have this cantilevering shear wall that we model as fixed base on the left, we have the superstructure movement and displacement at the roof, call that delta W. If we model that with springs and account for the movement up and down as the soil deforms vertically, then that will translate into additional horizontal displacements up the roof, the delta F, and that increases the total displacement. That will increase the period, and that will change where you are along a response spectrum. So for example, if we are a short, stiff building on the left here, and we increase the period, then we might climb up a site-specific response spectrum and actually increase the forces at the first mode. On the other hand, and a little more likely, if we're on the downward side, on the right-hand side, and we increase it, then we'll go farther down, and we can tend to decrease the spectral accelerations that the building is experiencing. Now, this up and down movement of shear walls or brace frames can not only change the period, but can change the way the building behaves, sometimes in very fundamental and really important ways. So here's an example. This is taken from the ASC 41 design guide and slightly modified, but in the fixed base model, you can see that deformed shape at the top there. And the critical element is the bottom story compression brace that has, it's highly overstressed. So utilization ratio is the Perform 3D weird term for demand capacity ratio, and it's highly overstressed. It's way over 1. So the kind of the weak link in this is compression buckling. But if we model foundation flexibility and put in vertical springs here, you can see how in the bottom picture, it has a totally different look, right? We're kind of rocking those brace frames, and the demand capacity ratio dramatically goes down in that compression brace. We get more movement in the beams and the connection of the beams to the braces, but we get less of a demand on the brace frame. So in this particular example, a fixed base building fails and a flexible base building works. That's a pretty big deal. It's not always going to be this way at all. We didn't actually fake it to try and make this happen. It just actually happened when we did the example, and we were sort of pleasantly surprised. But it shows you the value sometimes of just modeling, even in simple ways, foundation flexibility. So, you know, you can kind of extend this to other systems. So we were looking at brace frame. Now you could look at a shear wall. So in a fixed base or a really stiff, strong foundation picture at the top, the shear wall being the stiffest element is going to take the bulk of the loads. It's not going to move very much, and the adjacent columns and beams have small displacements, smaller demands, less damage. Conversely, if we rock that shear wall and that relieves some of the forces it's experiencing, that rotation has to go somewhere, and those increased displacements can harm neighboring elements, particularly if they're non-ductile, say non-ductile concrete buildings, you know, kind of like what's shown here. So we developed this rule of thumb. This was actually John had proposed this in the TC83 project, and then we kind of fleshed that out in a little more detail and a little more specific. So we have some very step-by-step rules, but it kind of boils down to a pretty simple idea. This is attempting to capture that structure stiffness to soil stiffness relationship, and you just need to know 3 things, 2 of which are pretty easy. One is what's your effective height, which is to the kind of centroid of the building. So this is nominally done at 2/3 of the height plus whatever the depth of the foundation is. The period, and we're just using the code equation that we use to design the equivalent lateral force method. And then you need to know the shear wave velocity, which you either can get from the geotechnical report if it's done, or you could extrapolate it from site classes and their definition. So you plug those 3 numbers in. If that number is bigger than 0.1, we sort of deemed that you're likely to have potentially important, significant SSI inertial effects. So it's a chapter on base slab averaging. One of the things that you need in addition to a big base is you need to have things connected together. So in the bottom right picture, if you had a continuous mat foundation and you know, everything is connected, it's a big, strong, stiff guy, then you're in good shape. You know, unless you had a very strange thin mat, which you wouldn't, then you definitely qualify for base slab averaging. But in picture A, one way to build a building is to have that slab have blockouts at the columns and have a soft architectural sealant around there to keep the water out. But there's no direct engagement of the footings or connections from one another, even through the slab. So you don't get to use base slab averaging. So these pictures don't exist anywhere. And so we added things like this for a practicing engineer to say, you know, which one of those guys do I have? And then, you know, do I qualify really? So it's kind of like the commentary that's sort of missing in the codes that we have. So let's do kind of a little example to show you the impact of that. So if you had a building that was 100 feet by 400 feet, so that's a pretty big building in my world, and you just take the square footage of that, you take the square root of that, that's the equivalent square, that gives you the length on a side, that's 200 feet in this case. That's below the max that you can use, which is 260, which comes from kind of empirical data of what we have available from actual measurements. And then there's some equations which I'm not showing you, but they're not that hard. And you can see the difference. So the solid red line is the original spectrum, design spectrum here. And the dashed line is the reduction that accrues with this particular 200-foot building. And you can see, remember I was pointing out, it's a bigger deal in the short period range, and then it becomes essentially nothing when we get out to the downward velocity driven slope. But if you were in that, short period range, you could take advantage of this and get a reduction on your design forces. Embedment's very similar. So here's another one of these pictures where we're showing kind of a real example of a building, and what do you do when it's on a slope? So you take the lower embedment, the one on the left here, and then you can't go more than 20 feet. So again, this is one of these sort of, limits in the provisions. So 20 foot is what you would be plugging into equations and making sure that you had, the value that it was the full at least 75%, and that would be what you would plug in. So if you did that, then, here's a similar pair of response spectra, and you can see how they have a similar look to the base slab averaging version, that it's primarily in the short period region. So you can combine these effects. If you had a big building that's embedded in the ground with the basement, then both factors accrue. You basically multiply them together, but you can't go lower than 0.7 in ASC 7. So you can get at least 30% reduction, which is kind of huge, but you can't go below that. So in order to, model springs, you need to have some, techniques, some provisions, some values for that. ASC 7 doesn't tell you how to do that. ASC 41 does, and so do these other documents that I'm listing there. And here's some examples of different ways people do it, like the most simple one at the top where it's a concentrated spring, and then other versions in there. So we have a chapter sort of synthesizing that information and showing you a worked example on it. Period lengthening, here's an interesting and fairly dramatic example showing you the difference between fixed base and flexible base. So what's on this screen? There's a lot of info on the screen, but let's start with the table on the left. So we took 3 types of buildings: 3-story shear wall, 10-story shear wall, 10-story moment frame. And we've modeled them with fixed base, and then we've modeled them with flexible base conditions. And so you can see the period, if you can read that on your screen, the period of the 3-story shear wall building was 0.19 seconds, so very short. And then when we include soil flexibility in there, it more than doubled to 0.49. Okay, so up on this response spectrum, that's the blue line on the left. So we started at the open square and went up, and we kind of hit the peak. So the forces would go up in this case if you were using a spectrum that looked like this. But the 10-story shear wall one was already a longer period to begin with, and then when we put it and allowed it to rock, it significantly increased. It doubled the period and went down the spectrum. The moment frame was less impacted because a moment frame isn't as sensitive to rocking. Chapter on foundation damping, which talks about those 2 different kinds of damping. There's 2 different sets of equations. They are soil damping, very easy, simple equation. Radiation damping, a lot of work, many, many steps. So we have a long kind of step-by-step, do this, do this, do this, in the order that makes sense rather than the way the equations are written in ASC 7 or 41. You can't use this for deep foundations. It's a shallow foundation kind of effect, and there's a limit of up to 20% damping. So, going from your 5% that we're used to using to 20 is actually a huge difference. But there's a floor on how far you can go. The chapter that we included on how to model basements includes some, I think really important work that the ATC 83 project, this NIST document, had developed, where we did a baseline model, the one on the right, which was sort of our fanciest substructure model with variable depth springs horizontally, different kinds of damping in there to really try and do our best job of modeling it. But it's not something you would typically do in practice. And then we compared that against all these other simpler techniques to see which of the simpler techniques was a close predictor of the best model, the baseline model. And so what we found is that the most basic one, where you just fix the bottom of your building, get the loads out of that, and then throw them in a second model to design the foundation, doesn't do a bad job for moment frames. Doesn't do a great job for shear walls, but it works for moment frames. The second model, where you ignore the dirt, you include the basement plus the superstructure, and you fix the bottom of it at the bottom of the basement level, actually is a pretty good predictor both for moment frames and shear walls. And then there's another sort of what we call a modified bathtub model, that model 4 simplified, that also does a good job. And this is the one that's in the peer TBI document, that model 4 simplified. So we have some worked examples in the design guide that show you some numbers. So one is for that model 1, where we have 2 models. We fix it at the ground with restraints. We get the loads out of that, and then we impose them on the foundation. And this is sort of the traditional code approach. I'm not showing the ratioing of by R values that's code required if you have different R's, but that's not the important point here. So model 2 is where they're all combined, and the shear walls in the basement and the brace frames above are together. And we show you the subtleties of how to do this. So this is actually kind of a tricky thing about where you scale and where you compare things. You need a little bit of acceptance of your building official to really apply this. But this is, in my opinion, the right way to do it. And I have generally had this approved by the authority having jurisdiction. So you don't need to see all the little values here, but what the point of this table is that I've been mentioning ASC 7, new buildings, ASC 41 for existing buildings. They both have SSI provisions. They both cover most of the same things, but they're not identical. So it's good to appreciate that, and usually ASC 41 is a little more forgiving, a little less conservative. It has fewer limitations. Not in every case, but in most cases. I mentioned that we had these appendices for detailed examples, many pages, many issues. So here's a 2-story buckling restrained brace frame building sitting on spread footings. So we show both horizontal and vertical foundation flexibility, how you derive those equations, how you would put them into this model. And then we show the implications of soil damping, radiation damping, and base slab averaging. And then really importantly, we also show the limitations of how far you can take these things and what you would really get in terms of the difference in the sizes of members. So we have a fixed base result, and then we have different flexible basis results to show you what the footing size and the brace size, how they would change depending on whether you included or didn't include these effects. And similarly, we did the same thing for a taller dual system building, concrete building still, but shear walls and moment frames in one direction and moment frames in the other direction. And we've got a whole host of other SSI effects that we covered in there. So I'm going to wrap up here with just some final tips from both from my point of view, but I think from the authors of the design guide point of view as well. So a little reassuringly, after you've got a design guide like this, or you've gotten your feet wet, I don't think most SSI is that hard to implement. It looks a little daunting if you haven't done it, but once you've kind of got in, like a lot of things in life, it's probably easier than you would have thought originally. One of the drawbacks of it is that it's often iterative. So in a fixed base analysis, you fix the base, you run the model, you get the results, you design your elements, and you don't have to iterate. You could, but you don't have to. But a lot of times in SSI, we need to converge on some results, and so it can take a couple more rounds than it would have. Most of the time, it's, when we lengthen the period, you're going to go down on that slope. But if you have the one I showed you and you were going up on a site-specific spectrum that didn't have short period truncation, then you could get an increase in loads. Hopefully you're kind of convinced that there are some buildings that are sensitive to rocking where you could get a really big difference in what happens if you account for that rocking behavior. And we showed you some pictures, so I hope that's an important takeaway for you. And then shear wave velocity, which I didn't talk really at all about, is actually a pretty subtle thing. And there's a whole host of different versions of it and different ways it's defined in the different situations. And that's really hard to parse and understand in the building code. So we try to do a good job of explaining that issue and how to get the right one in there. And that has actually led us to some code change provisions that are making their way through the next edition of AC7 pretty much because of this project. And then I had mentioned there's limitations, and ASC 41 is a little more relaxed. So I will end there. And thank you for your attention, and look forward to questions towards the end of our session. Turn it back to you, Jorge.
Thank you very much, Bret, for this very neat and clear presentation. As a reminder, the webinar is being recorded. And as Bret said, the questions and answers will be at the end of the 3 presentations. Our next speaker is Dr. Sissy Nikolaou. Dr. Nikolaou leads the Earthquake Engineering Group of the National Institute of Standards and Technology, NIST. Her group develops, advances, and deploys measurement science to reduce seismic risks to the built environment, and supports the National Construction Safety Team and National Earthquake Hazards Reduction Program. Prior to joining NIST, she was a consulting engineer for 25 years with global projects involving critical facilities, lifelines, and high-rise buildings. Dr. Nikolaou.
Can everybody hear me?
Yes.
Yes. And you can see my screen, right?
Yes.
Okay, wonderful. Thank you very much, and thank you for the invitation to present in this great event. I will continue the conversation on SSI on a more trends and philosophical level, I would say, of how can we connect soil structure interaction challenges and solutions to the new concepts of functional recovery. So as we all know, our codes have a fundamental concept of life safety. And I wanted to show you this example, especially since this event is named after Professor Ishihara on liquefaction. This is a house where life safety objective has been met over and over again in the events in Christchurch between 2010 and 2011. This is a residential house that Professor Jonathan Bray from UC Berkeley monitored in the different earthquakes that happen. And as you know, there was repeated liquefaction from which we learned a lot. But look at this house. Liquefaction happened in the first event. The owner fixed it, sun boils again in the February 2011 event. Then he put pavers to hold the ground down. And this did not do any good, obviously, for liquefaction. In April then in June, and again in the second part of June. So you can imagine the mess that was happening inside that house, where structural safety had been satisfied. And not only that, you know, this situation put this and many other residencies in the category of a flood zone because of the groundwater levels after all these settlements that happened. So the houses lost tremendous value, and there were a lot of problems with insurance that I'm not going to go into about flood versus earthquake insurance. So life safety was satisfied, but not necessarily life quality. So I think we are at the point of having used life safety for decades now, where the society is kind of demanding something better, something more. We can call it the R word of resilience, or what we usually associate with, which is a bounce back strategy. I would rather go forward to something better than what you just saw in New Zealand. So life safety concept is no loss of life after an extreme event, which is of course what we all want. The structure can give you an opportunity to get out of it alive, but it could be heavily damaged, and it could even have to be replaced, even with the newer codes that we have. So where is life quality on all that? I find life safety to be a little of a deceiving factor, because safety means that I'm doing better, you know, at least for me. So it is more about how our lives are going to evolve after an earthquake. And that has to do a lot with how well do we go back to functionality, regain our services, and eventually our daily lives, as we have unfortunately seen in the past year with COVID. So the codes, especially with a report you just saw, are evolving, and soil structure interaction is becoming more adapt to the conversation between structural and geotechnical engineers. So we are trying to move from conventional, very prescriptive guidelines, especially for geotechnical problems. I think in the structural domain, this field has evolved and has taken a lead for reasons that have to do with, you know, a lot with uncertainties in soil versus structures. We have evolved to a more progressive, sometimes more abstract, performance-based concepts, like where we are looking at behavior and risk and consequences, and whether those are in acceptable levels for different levels of earthquakes. Still, this concept is going to get in codes up to a level of safety or reoccupancy, as you can see in the known possible post-earthquake states. So here comes the next generation of functional recovery, where functional recovery is defined as an objective that can be achieved within acceptable time following a specified earthquake. And this acceptable time may be different for buildings or lifelines. And it is a post-earthquake performance state in which a building or lifeline system is maintained or restored to safely and adequately support basic intended functions associated with how things were before the earthquake. So I tried to put something similar for a geostructure or a dam or a slope as to how this would look like. But it is so much more general than that, because in order for a building to function, the services to the building have to be there, and everything has to be connected. So it's not the isolated structures or geostructures anymore that we have looked at performance-based design. So a report by NIST and FEMA was published earlier this year that defines in greater detail what the main needs are to move to a functional recovery framework. And these needs are summarized by 7 main recommendations in this report, which is available. This was a big study that was managed by the Applied Technology Council on behalf of NIHERP, NIST and FEMA, and came up with several recommendations in response to the reauthorization of NIHERP. With the first recommendation is that we need a functional recovery framework. And the blue and the gray recommendations that you see have to do with the physical built environment, where it's the infrastructure at large, meaning buildings and lifelines. So for new and old buildings and lifelines, we will need to define what are recovery-based objectives in terms of time and other criteria. But also there is a huge factor that is socio-environmental that has to do with how do we define recovery-based objectives in terms of planning, what are the needs for education and outreach, and where are the financial resources to implement and put all of this in place. So I would encourage you to take a look at this, and this is what my presentation will be focusing on as the next frontier of soil structure interaction, and not only. So functional recovery, if you think of the overall big community resilience goal, where you look at what is going to happen to clusters of buildings, services, or whole lifeline systems, which is much more than codes, where the codes, you see them on the left, could be prescriptive or performance-based design, but they're more isolated. The bridge between the two, we consider to be the functional recovery, a link between design, construction, and retrofit of assets to what we call community resilience. And it's more about systems, but not a whole community of systems. It's more of an engineered goal that we can hopefully quantify through recovery times. With that, I would like to connect some concepts and some aspects of our design that involve soil structure interaction or geotechnical earthquake engineering to functional recovery. So what are some facts that we know is that recovery times or downtime can cause multiple times of the loss of the immediate structural damage, as we saw in Hurricane Sandy, for example, that had not only local major effects that we see to date, but also global effects. So imagine that you shut down Wall Street, which is what happened, what the effects are on a global scale. And I'm using a hurricane, but it's the same for earthquakes and other hazards. And when we're talking about functional recovery, we have to think of also cascading hazards. The other mega trend that we have, particularly for our infrastructure lifelines, is that we are dealing with climate change. And climate change has to do with slow processes that we can call them chronic stresses that are eroding the soil or creating slow evolving processes that can create more vulnerable subsurface. For example, very frequent effects, and this is an image from the 2016 Muisne earthquake in Ecuador, where I will show what happened after frequent events when the earthquake occurred in a landslide. And we also have acute extreme events that could be initiated by climate. And this is our new norm. And this may not damage specifically an infrastructure system, but it can create lack of access to that system, which is going to affect functional recovery. And lastly, what we have seen is that now the maximum event may not be the most detrimental for a system or even for a geostructure. And that has to do with partially in the tremendous growth in population, where we are forced to build in marginalized lands. So the perception of risk now is changing, because with repetitive small events, even if they're not driven by climate changes, could have detrimental effects because of the exposure of population, because of the higher urbanization that we have to do. Should geo-professionals care about this? I mean, we should all care about this. ASC just released the failure to act report. That's another report that would be great if you would like to see it if you haven't done so. So for what ASC said is that until, if we project to 2039, our overdue infrastructure bill would cost each one of us $3,300 a year. And they have a lot of cool stuff about what you can do with this money instead of spending it on that. And moreover, tremendous impact on our GDP and jobs and all that. And of course, there is the good news in all of this is that if we act now, as the process seems to be, is that we can reverse that process before it is too late. So lifelines, and particularly buried lifelines, are in the key of all of this. And these have to do with soil structure interaction in terms of evaluation, but also retrofit solutions, because obviously we are running against time and we are racing against time. We don't have the time and the funds to replace the infrastructure. So we have to find smart solutions. So how do we do that? How do we migrate from performance-based design to functional recovery frameworks? Definitely soil and structure have to work together as a system. But also the interconnections between other hazards, the interdependencies of one hazard to the other, for example, fires after earthquakes. What we need to do is we need to use the tools we have of innovation, instrumentation, visualization to understand risk and to reevaluate risk periodically based on data we collect from instrumentation and lifelong monitoring to reevaluate our risk because the life cycle of each asset rapidly deteriorates. And we have to incorporate functional recovery goals into decision-making and also look at these more frequent events and look at how much our assets can give us back and find ways to present this as a business value. And one of the ways to present this as a business value is to fit it with optimization of the day-to-day maintenance funding. And that is very, very important. So all these functional recovery concepts can come together to support decisions. There will not be a one-way street of an optimum in this conversation. We need to develop tools to explain different decisions as a risk versus investment conversation, and also life cycle expectations in our frameworks. Obviously, it's very complicated, right? So I would like to talk about some challenges that I have seen that are in the way and some solutions that could overcome them. So one of them is that we need to do a better job in communicating. So I just heard in the previous presentation, somebody calling soil dirt, which would be a very bad word for a geotechnical engineer. And it's always, this big issue, like why can we work together? Why structural engineers always consider soil a spring, and geotechnical engineers consider structure a load. And we know that you just heard it's not it's an iterative process. We live in a nonlinear world where properties of soil and structure change depending on the levels of the strains. The damping is changing based on these strains, and we have tools to evaluate those and understand them. So, and we also have great tools to communicate risk, and maybe we are not doing such a good job in doing so. So I wanted to show you a great example of visualization. This is a repeat of the 2001 earthquake in Seattle to support decisions for the Alaskan Viaduct. So what you see here is a few years old. It was made what was Parsons-Brinckerhoff, now WSP, from many aero photographs of the Seattle waterfront and a simulation of the viaduct as it was by in different nodes, time histories of each of these models that you see have been developed by engineers and have been peer-reviewed in the University of Washington in order to show to stakeholders and decision makers what liquefaction means, what strong ground motion shaking means, not just to the infrastructure, but to the lifelines, to settlements, to looking at lateral spread, and of course, at some point, failure of the gas pipeline systems that leads to subsequent fires past the shaking and tremendous destruction. What you don't see is the inland behavior because that was not modeled. So this video took over tons of reports and supported decisions. Of course, it's scary, but sometimes the message is not pleasant, but it is consistent and truthful. And that is what puts all of us on the same boat of trying to make the best decisions for our communities. I believe that there is a tunnel now there in place of the viaduct. So what else can we do with soil structure interaction is to try to push the envelope a little bit, think differently, and think about how can we incorporate the R's of resilient designs, which would be redundancy, resourcefulness, robustness, and rapidity. So what seems to be the same in the concept of a code, which we know it's just a minimum standard that we need to follow, does not necessarily behave the same in repeated earthquakes or in big earthquakes. So here is an example of a mechanically stabilized earth wall that has been designed with a retaining wall that has been designed either with mechanicalized stabilized earth on the right or conventional tangent pile wall. The soil properties that you see on the green are of the backfill soil is the same. Everything is the same other than the design of the wall. Both systems have been designed for a static factor of safety of 1.8 and a peak ground acceleration of 0.16, for which the pseudo-static factor of safety is 1.2. The MSC wall on the right has reinforcing that is spaced at about 60 centimeters apart. And apparently, these two systems have the same pseudostatic and static factor of safety. So when you look at their actual response in two levels of earthquakes, one is a smaller earthquake close to design, and one into more of closer to the MCE event. So on the left, you see the response at the top of these walls. Red is the pile wall, the conventional wall. Green is the MSC wall. And you see the response to the Loma Prieta Gilroy record. At the top of the wall, you see a displacement of higher for the conventional wall. Still, you must be within the okay limits for the wall to sustain these loads. But when you go to a twice as big ground acceleration and much stronger shaking with a Northridge Rinaldi earthquake, you are reaching more than you're reaching more than half a meter on the conventional wall. That is not going to make it work okay. And it's by far superior is the MSC wall. So in that case, you know, if I was wearing my hat of the consultant, I would say that this wall has a lot of capacity and it could save me a lot of money. I could go and spread the reinforcement more. Instead of 60 centimeters, maybe I can have it every meter or more than that and save a lot in reinforcement. Or I could go and start looking at this, killing it to the research and try to make things happen. That's what we are trying to do. We're trying to bridge these two and use good science, use the numerical tools, the simulation tools that we have to validate this performance that we see. Why is it superior? It's superior because it is robust, but it's also redundant and it's resourceful, right? So we use the analytical tools, and I think these are Abacus analysis. This has been done by NTUA at Dante universities in Europe. And what you see is the strains inside the soil and inside the reinforcement for the original design on the top. And what you see on the second, where I wanted to save money, is that if I spread the reinforcement, then I am putting a lot of distress in the reinforcement, and especially at the foot of the wall, which means when the next earthquake happens, probably I'm not going to be redundant anymore. Probably I have taken what I could take from the anchors, and I would probably not have such a good behavior as with a full reinforcement. And of course, we have seen in earthquakes like in Kobe that stronger is not obviously always better. And this is where the ideas by Professor Carter and Professor Gazeras have come on creating plastic hinging intentionally on the subsurface in the footing in order to relieve the loads from the superstructure. And of course, that has been an anathema of designers. You know, how could you do that? How could the foundation not have an R equal to 1? Well, because it's not practical, and because behavior-wise, as a system, you are penalizing so much the superstructure that you're making it very brittle and not robust. So this is to be done, right? It's not done yet. So in terms of using our rapid reconnaissance technologies, I wanted to show you what happened in Ecuador. After a lot of rains, an earthquake happened on April 16th and created a 3-phase landslide that was massive, and for which we collected a lot of data, including thousands of drone pictures that were running irregularly there. So we collected maps from Google on how the slope was before the earthquake. And then we created a cloud of the images of the drones so that they are compatible to create a 3D model of the slope after it failed. And this is how you see it rotating. So what does this help us with? We have this DEM, the digital elevation model, from the landslide that if we overlay with the before image, then what we have is true volumes being calculated automatically. So this was an effort done as a result of a gear mission that also the same group that created the video was able to put all that together, and with a relatively fast and easy macro in the 3D CAD software, we were able to develop sections and be able to have volumetric changes very fast. And this is a section that you can easily cut with your mouse and immediately get slopes and volumes from these drone images, something that would take months to just get a couple of them. So with that, we were able to combine ground motions that were nearby and soils information in order to understand and study this earthquake better. So I'll go quickly through some basic stuff that we need to think of when we are putting all these systems together, and our thoughts about how do we recover is to think about multi-hazards. And the example here is from flood protection and the concept of raising the foundations in order to be on a higher level when the flood, the new 100-year flood comes. And that is great for floods, but if you look at earthquakes, like in this very fancy building, this creates the perfect soft story. So we need to think of both, and it goes the other way too. As we intervene for earthquakes, we need to understand how are we affecting the other hazards. Also, we have to respect the geology of an area, the geologic history, and the geotechnical investigations. This is an example from the Chichi earthquake in Taiwan, where this was a good, well-designed bridge, but in a very bad place on top of a fault. Where if there was geotechnical team in place, they should have brought this up, obviously. So where do we go from now? I hope that this steers a conversation about how we can work together to reach these frameworks and these goals, right? So where are my takeaways on steering this conversation is that we need to have a basic engineering understanding of the behavior of systems above and below ground and how they work together. We have to validate and calibrate computational models and test them also in small and large scale in order to make innovation our practice and reach the functional recovery goals and incorporate reconnaissance lessons that now we have a lot of observations and organized data and map data. And typically we study why things failed. But when you look at resilient behavior of structures, geostructures, infrastructure, we have to look at things that did not fail, although they should have failed. And we do have those. It's just that they are not as attractive as failures for us engineers, right? And innovation should include new materials, new concepts, construction methods that can provide redundancy, again, with proper validation. And we have to always have in mind, we live in the era of climate change. We need to think of multiple and smaller events and we need to understand the exposure of the population to these hazards as the population grows. And these concepts have to be in place in order to demonstrate the business value of looking at all of these by offering cost optimization in the allocation of the budget that is always very limited versus what we would like to have. And most importantly is to communicate and collaborate not only among engineers, but also with all the other disciplines, including stakeholders and of course the public. With that, I'd like to just say that investing in functional recovery and overall community resilience is an obvious choice because it works. And maybe it's the only choice because the alternative is no longer enough since we have major challenges to deal with. There is a recent FEMA report that is very interesting that shows the value of building codes that has elevated the return of investment in hazard mitigation from $6 to up to $11 for every dollar spent. And this is something that we need to learn to convey to our clients and to government when we are proposing solutions that mitigate hazards. And finally, it is not as civil engineers, we have not only the choice, we have the social responsibility to consider these types of designs because they're going to eventually move us using functional recovery from life safety objectives to life safety and life quality objectives, which is something that we owe to our kids and to the society, right? So for wearing the hat of the geotechnical engineer, I must say that geotechnical engineers have demonstrated leadership through innovation that can be applied. Innovation is part of geotechnical engineering because every problem is different, every subsurface is different. So this mindset can be used for multi-hazard frameworks together with structural engineers and especially give solutions for aged infrastructure lifeline systems. So with that, I will leave you to, and I will see the questions on the chat. And thank you very much for the time.
Thank you very much, Dr. Nikolaou, for this excellent presentation. So our next speaker is Professor Jonathan Stewart. He's a professor in the Civil and Environmental Engineering Department at the University of California, Los Angeles, where he's been a faculty member since 1996. His technical expertise is in geotechnical earthquake engineering and engineering seismology with emphasis on soil structure interaction, ground motion characterization, performance of levees and other embankments, and ground failure. His work has impacted seismic guidelines and policy nationally and globally. Examples include the US National Seismic Hazard Maps and recommended procedure for the seismic assessment of structures. He's a former chief editor of the ASCE Journal of Geotechnical and Environmental Engineering and is now the past editor of Earthquake Spectra. Professor Stewart, please.
Thank you, Jorge. It's a pleasure to be with you all here today. I'll be talking about seismic pressures on retaining walls. So I think this fits quite nicely with the two presentations we've heard. One of the things that Dr. Nikolaou said in her conclusion was that we need to understand the fundamental processes involved in the problems we're working on. And I think as I go along, you'll see this very much fits in with that. And this is also an extension of some of the SSI principles that are in the ATC guidelines documents that Bret was talking about to the problem of seismic earth pressures. So it's a good fit. What I'll be going through is this outline. I'm going to introduce the topic and why we've been working on this. Then I will talk about what we have observed in earth pressures when we have been able to actually measure them. So this usually involves some kind of test or analysis. I'll spend most of my time on modeling, and I'll be making the argument that the development of pressures that are significant or maybe rather modest on retaining structures is a soil structure interaction problem. And that may seem like a kind of obvious thing in the context of this meeting, where we're talking about soil structure interaction, but that's not really the way that we've analyzed it historically. And so to move in this direction in our practice would represent a significant change. And then I'll have some summary remarks. So retaining structures, generally speaking, with few exceptions, tend to perform rather well during earthquakes. So Sissy mentioned gear reconnaissance. Many gear and other deployments after earthquakes have looked at the performance of retaining structures. And by and large, even when you're in areas with very intense shaking, they tend to do pretty well. But there are a few exceptions. One of those exceptions was actually made reference to by Professor Ishihara, and that is key walls, particularly when you have liquefaction. That's a known major problem that has to do with liquefaction undermining the foundation support and increasing the earth pressure. And another example is when you have retaining structures that really don't have any kind of bending strength or tensile strength, and you can have toppling types of failures like this wall in Italy. Despite that generally good performance, we do require, in many contexts, the consideration of earthquake forces on our walls, even though many of the walls that have performed well really didn't have much seismic design in them. And one such example guideline is this NCHRP document having to do with highway walls and highway construction generally. And I think this is a good idea to have some codes and standards. I'm not claiming otherwise, but I do believe, as I will explain and comment on here, that I don't think the way we're doing it now is the right approach. So if we want to look at seismic earth pressures on walls, there's two options. So one of them is the direct analysis, and Bret showed the same figure, which is from the NIST 2012 report, and it just kind of shows, as he explained, all the different elements of a soil structure interaction problem in a single analysis. You have the structure, you have the foundation and the gray hatching here, which is modeled by finite elements, interface elements between the foundation and the soil domain is excited by an incoming wave field, and the whole thing is analyzed in a single step. So if you're doing an analysis like that, you will capture in a very natural way the pressures that develop on these walls. And those pressures can be because the structure is responding and there's inertia going in there. And it can also be because you just have waves going up and down through the soil medium. But also, as Bret explained, we don't usually do that. For most structures, we don't do sophisticated finite element analysis, and we do more simplified methods. And in this subject of retaining wall pressures, the way that we typically do it, including in that NCHRP document, is something that I'll call limit state analysis. And in these limit state analyses, you essentially have an assumed geometry of a sliding wedge behind a wall. You have the normal non-earthquake forces, the weight, the reaction down here, the active earth pressure, if it is a wall that's allowed to move a little bit. And then you introduce a horizontal seismic coefficient that is related to the PGA, and then that causes a seismic increment on the pressure PE. And so we can work out the equilibrium of this and essentially relate KH to the cumulative reaction here. So this was originally formulated by Okabe and Mononobu Matsuo in the 1920s. So this goes back a long way. And this is a relatively modern presentation of that by Kosecki, in which we have the seismic, actually it's a combination of the static and seismic coefficient here, KAE. It's the two forces summed and made dimensionless through this normalization down here, basically 1/2 gamma h squared. And you see how this combined coefficient is increasing as the horizontal seismic coefficient goes up. So this is nominally related to PGA. So for example, if you have 0.4, you've gone from about 0.12 up to about 0.3. So almost a tripling of the resultant force on the wall. The other important feature is that these curves, by virtue of how that equilibrium problem is solved, do tend to go towards infinity when the ground motion gets sufficiently high. Now, one simplification of these relationships that was proposed by Seed and Whitman takes the delta KAE, that would be the additional increment from the earthquake, as 75% of KH, which basically plots as a line like I'm showing here. And that has a couple of advantages. It's, first of all, very simple. And a second advantage is that since it's a straight line, it will continue to be a straight line no matter how far out here you draw it, which means it remains numerically stable even when the ground motion becomes large, and the underlying theory would predict infinite earth pressures. Okay, so let's talk about what we actually observe. And by observation here, I'm not talking about just observing walls doing well or not doing well. Those are, of course, observations, but we don't know specifically what the pressures were. So what I'm going to be talking about here are pressures where we can actually either measure them or calculate them. So that'll be through centrifuge modeling, measurement, or dynamic SSI, essentially direct analysis, where we compute it. And one of the classical, I think we can now call this classical tests of this. This really spawned a whole series of additional tests and insights on this topic. This was done at UC Davis by Linda Alatik and Nick Sitar. And in a series of documents, a report and a paper, they show what happens with this model down here, where you have two U-shaped walls. One of them is relatively stiff in terms of the structural elements. The other one's relatively flexible. And the dimensions shown here are in the prototype. So in other words, once it's spun up in the centrifuge. An important detail is that these walls have soil underneath them. They're not resting on a rigid base, so that allows them to rock in a natural way as the earthquake passes through. And they run 3 different time series through it. One of those time series was a ground motion from the Loma Prieta earthquake. And I don't want to spend a lot of time on exactly how they measured these pressures, but suffice it to say that they inferred pressures in 2 different ways with different types of sensors, which is shown here by the symbols and the dashed lines, basically. So the data from this particular test is contained here, where we have depth and pressure. If you apply the Mononobe-Okabe method to this, given the PGA that they recorded in the centrifuge, you get a result like this black line. So they observed, obviously, that Mononobe-Okabe, or the limit state, is over-predicting. And they found that for this particular earthquake, if they use 65% of the PGA, it's pretty consistent with the observations. They also tested 2 other ground motions, one of which I'm showing here from Cacelli, where the same process was undertaken. Again, there's an over-prediction. If you apply the 65% rule, it's still over-predicting. You could apply a different factor, maybe something like 50% would work in this case, and then you would again get a match. But the point here is you would have to apply a different factor for every ground motion in order to get the theory to match the data. So the takeaway message from that I took anyway from this series of very useful experiments is that the total earth pressures are below the Mononobe-Okabe predictions. And subsequent tests, there were a whole series of these ran with different PhD students, essentially consistently found that the limit state methods were always over-predicting what was measured. Now, some methods to sort of massage the PGA a little bit were introduced here, but the straight Mononobe-Okabe procedures were over-predicting. So the next set of observations I'd like to talk about are dynamic SSI analyses. There's been many such studies. I've listed some of them down here. What I'll talk about is one study by Farhad Nostadon, 2005. He has a rigid wall, he has elastic soil, and a rigid base underneath where the ground motion is input. That ground motion is broadband, and what broadband means in this context is there's energy across a wide range of frequencies, including at the frequency of this elastic soil medium sitting on top. So in site response, if you excite a medium with a rigid base, and you have some energy at the fundamental frequency of that medium, you're going to get a very strong response through here, a very strong modal response with a great deal of amplification through there. That's going to produce pretty large pressures on these walls because they're rigid and they're not allowed to rock or move with the soil. And so if we look at this snapshot of Ostadon's results, these are his computed earth pressures as a function of depth for many different ground motions. And the Mauna-Obi-Okabe solution is this black line here. And you see that the Mauna-Obi-Okabe is under-predicting. Remember, before it was over-predicting. Here it's under-predicting what was computed. So if we summarize this series of observations, and I should mention also that Ostadon's results are typical of other findings as well, so he's not really an outlier in that way. We have centrifuge tests providing pressures that are appreciably smaller than Mauna-Obi-Okabe. We have analyses of walls with these particular conditions that have been very widely looked at in the literature, which provide pressures larger than Mauna-Obi-Okabe. So there's agreement that Mauna-Obi-Okabe or limit state methods don't really work, but do they work in the conservative direction or the unconservative direction? There's no consensus on that. That leads to a considerable degree of confusion over whether these methods are reliable or not. So that leads me then to what we're proposing. So we were motivated to see if we could resolve these conflicting findings from the literature by taking a more fundamental approach to understanding why actually we see earth pressures or we don't in a given situation. And this is fundamentally a soil structure interaction problem. And so the rest of this presentation will talk about how we can use soil structure interaction to understand these pressures. And we have developed this sufficiently that we have what we think is a practical model that can be used. So the SSI-based modeling, as Bret introduced, there's sort of fundamentally two pieces to it. There's inertial and kinematic. Either one of these can be the controlling source of seismic earth pressures in different situations. But what they have in common, and this is the single most important takeaway from this presentation, is that what is really driving seismic earth pressures on walls is whether you have relative wall soil displacement. Where you have relative wall soil displacement, you get earth pressure. On the other hand, if the wall and the soil, for whatever reason, are moving more or less together during the earthquake, then there's no pressure. It's as simple as that. So that's the basic concept. The tricky part is, when do you get large relative displacement and when do you not get it? And so we'll look into that going forward. Start with the inertial part. So a really important consideration with the inertial side of this is what is the path of lateral loads from a building structure down to the foundation? And does that path go through the basement walls or not? So if you have a situation like this, where the lateral force resisting system is the structural frame, and that frame is connected to basement walls, it's unambiguous in this case. It clearly is part of the system. These walls are in the basement. And so you will get an inertial contribution to the pressures because the walls are going to be pushed back and forth. They're going to deform these springs. And those, of course, are the pressures we're talking about. In another case like this, with more of a podium structure, you have walls off to the side. The foundations of those walls may or may not be well connected to the foundations of the core of the structure. The structure may have brace frames or a shear wall. that's carrying the bulk of the lateral loads, and it goes directly down to this foundation. And how much do these intervening elements distribute shear force or moment into the walls, depends on some of the structural details here. So it's hard to say in general in a case like this, but my point is that that would be the main consideration that you would have to work on in collaboration with the structural engineer to decide. So you could model that either using the direct methods that we've talked about or the substructure methods that Bret introduced for us. But those methods kind of already exist through the NIST report. Bret's report through ATC provides some very good practical guidance to supplement this 2012 report. So we have methods in our toolbox by which we can evaluate these inertial contributions. So I won't be speaking more about that. The work that I will mainly be talking about has tried to solve the kinematic problem for which we haven't had solutions. Okay, so that's what's next. So the kinematic interaction mechanism is just an extension of what Bret introduced with the foundation input motion. So I'll just remind you that we have a free field motion, the motion that would occur at the site if there was no structure. And then you have a foundation motion, which deviates from the free field motion because the ground motion is spatially variable, both in the vertical and horizontal direction, and the stiff foundation will average things out. Okay, so when this FIM is different from this, you're going to get significant earth pressure. When these two are about the same, you're not. So in order to help underscore that point, what I'd like to do is walk you through some simple schematics to help understand when seismic pressures develop under these kinematic conditions without an inertial contribution. So what we're looking at here is an element of soil without an earthquake yet. There's a vertical stress and a horizontal stress. And when a seismic wave passes through this, you see the deformation. For sure, that seismic wave will produce an acceleration. But that acceleration and the stresses associated with it will be carried on our element through a change in the shear stress on the horizontal and vertical planes. There is no change in the horizontal stress here. So my point is that you can have acceleration and have no change in lateral earth pressure. In fact, this is fundamentally what happens in all ground response analyses. Now, if we have a structure that's embedded below the surface, and in this hypothetical structure, if it has the same mass and stiffness properties as the soil, then it will deform exactly the way the soil does. And again, you'll have no seismic earth pressure because there's no horizontal movement that is different between the structural elements and the soil element because of the fact they have the same mass and stiffness. Now, of course, structural elements don't have the same mass and stiffness in real life. So if we have something that is at the extreme, which is rigid, now that has to move as a rigid body. It can't conform with what the soil is going to do. And so when an earthquake excites this, you're going to have this foundation motion, which is going to be different than the free field motion, as it says here. And because this motion and the motions over here are different, you're going to have an increment of lateral stress, along with the changes in shear stress and so on. So that's where you get it, relative displacement. So the key point is that seismic earth pressures are fundamentally related to the relative displacement. And notice that we get seismic earth pressures when we have relative displacement. We do not get seismic earth pressures simply because we have acceleration. You can have acceleration and no seismic earth pressure. So there is no fundamental link between those two. Now, the modeling of this, as we've discussed already, can be done through direct approaches. You would solve the kinematic part of this problem by simply removing the structure, and then you would get your kinematic earth pressures. But we're going to focus on simplified methods, and we've essentially tackled this problem over the last 8 years or so. When I say we, it's a whole series of collaborators that I'll mention at the end, in stages. In the first stage, we basically looked at a basic case involving a rigid wall, uniform soil. There's no inertia, so it's a purely kinematic problem. And we were able to develop a solution for this that can actually be expressed in a closed form equation. And that is paper 1 at the end. There are obvious limitations of that basic case because walls aren't rigid, soil isn't uniform, etc. So a more complete model was developed that relaxes many of these assumptions: flexible walls, flexible foundations, non-uniform soil, allowing wall inertia to be part of it. This was solved numerically and is presented in paper 2 with a workable model for it. In this workable model, you essentially run time series through such a system and calculate the responses. And based on the insights from all of that, we've developed a simplified model, which is paper 3. And it's this third one that I'll focus on here in the interest of time. So what I'm going to do in the next couple of slides is illustrate the basic steps associated with this simplified model. And then at the end, I'll highlight the fundamental physical principles that are captured, at least in an approximate way, through this method of analysis. So, but first, the steps. You need a seismic hazard analysis, and the best ground motion parameter, we think at the current time anyway, for doing this is peak ground velocity. And I would mention that in part because of this and other applications as well, USGS is now working on including PGV in the national maps. For a particular location, you don't just need the PGV, but you're going to need a period. In order to get a period, we're going to deaggregate, get the magnitude and distance that most strongly contribute to the PGV. Based on that magnitude and distance, we can use ground motion relations to predict a period. So here's such a relationship where you have mean period. This is essentially the central period, kind of the middle of what the ground motion and the free field is likely to have in terms of its frequency content. This is what we're trying to estimate. This is distance. And the different curves here are for different magnitudes, with larger magnitudes at the top, smaller magnitudes at the bottom. So if you have a magnitude 7, for example, at 15 kilometers on a soil site, you're at about 0.5 seconds or so here. Once you have that period, you can get a equivalent angular frequency through this relationship here. Next, we measure or estimate the shear wave velocity profile that's going to be in the backfill behind our wall. And we're going to calculate an average value of that shear wave velocity taken as the height divided by the shear wave travel time, where delta TVS is the shear wave travel time. You're just summing up incremental layer thickness divided by VS, summing it up to get the delta T. Okay, then we need to derive a ground motion amplitude. This is a displacement. We don't use PGV for a number of reasons. What we want is a displacement that corresponds to something more near the center of the frequency range that really produces energy. And we think PGV is the better parameter. So we're essentially converting PGV to displacement by dividing it by that frequency, omega sub m. And then in order to make that work through a calibration process, we multiply it by this factor. Again, in the interest of time, I won't explain the details of that factor, but it basically varies from about 2/3 to 1. So it's not a very big correction that we're making here. We need to represent the stiffness of the soil somehow, and this is done through a so-called stiffness intensity, KYI, which I'll just explain briefly here, since this is an unfamiliar term to most engineers. Stiffness intensity is simply stiffness, as we normally think of it, force per unit length, divided by area of wall. And so if you imagine there's a spring here, and there's a certain tributary area for that spring, dA, then the stiffness of this horizontal spring would be the stiffness intensity times dA. So it's a very convenient quantity in that respect for deriving our springs. So we call that stiffness intensity KYI. It has units of force per unit length cubed. And it basically is proportional to the shear modulus of the soil. The sixth step is that we estimate the relative soil to wall flexibility. We're trying to see how stiff our wall is basically in flexure. And so this beta is a relative stiffness parameter where the numerator, as you can see, is soil stiffness and the denominator is the flexural stiffness of the wall. And the ratio of those with the fourth root actually is not dimensionless. It has the dimensions of 1 over length. So we take that quantity and we multiply it by height, which takes the units away, it becomes dimensionless. And since this is not always known at the design stage, the geotech may not know what the section properties are. What we've done is we've looked at many constructed walls in consultation with some of our partners. Marty Hudson, for example, was helpful to give us some example dimensions for different cases, and we found that numbers in the range of 1 to 2 is fairly conservative. You can get lower numbers, but basically, if you don't know anything, you can use this kind of range to get started. And then this is essentially the result, and I'll kind of walk you through it. So you have here the earthquake increment of the seismic earth pressure, which has been normalized. You have here the height of the resultant, which you need in order to get the moment in the wall from the earthquake. The horizontal axis is the wavelength of the wave coming in divided by the wall height, and the beta H's here are the wall soil flexibilities. So that gamma over H, the wavelength to height ratio, we can get from the previous steps. It's basically the average shear wave velocity times the mean period for gamma. We have H here. And I mentioned that there's a closed form solution for this case. That was our first analysis. That makes that one kind of convenient. And in order to adapt that then for the other degrees of flexibility, we have these correction factors, which is, for example, the value of this result for beta H2 divided by this one for beta H0, which is rigid case. And so there's a chart showing this here, and there are equations for this that are included within our procedures. And this applies to both the normalized force, this one with the black line, and the wall height, the normalized resultant height, the red line here. So once you have this, you simply denormalize the force and calculate the moment as the resultant height times PE. So let's talk a little bit to wrap up about the physics that are represented here. We have the wavelength effect. So why does this go down? So essentially, if you have a low frequency wave that has a long wavelength, I've depicted that here. The motion here and here is practically the same. Under those conditions, this motion and the foundation input motion are basically equivalent. You're going to have very small relative displacements and negligible earth pressures. So that's the right side of that figure. And conversely, if you have high frequencies and short wavelengths, then this motion and this motion are very different. Large relative displacements, large pressures, that's the left side of the diagram. The other key feature here is the effect of wall flexibility. As the flexibility goes up, the pressures go down. To understand that, this is showing height, or basically wall height here in a normalized form, and displacement of the wall divided by displacement of the soil. Sorry, I misstated that. This is displacement divided by UG naught, which is the free field displacement at the surface. And this displacement is ground displacement in the case of the brown line, and it is wall displacement in the case of these other colored lines with different beta H's. So if the free field soil and the wall have a small difference, we're going to get a small earth pressure. If there's a large difference, a large relative displacement, we're going to get a large earth pressure. And so that's shown here, where the stiff wall with a small beta H produces a very large pressure. The more flexible ones with smaller relative displacements have much smaller. And so this effect is accounted for within the procedure. So this has been validated against a number of experiments, the Alatik and Sitar experiments, and a whole series of experiments done at Colorado Boulder, where you have the different results here, the peak seismic increments, plotted within this range for all these different tests or analyses, which go from beta H0 rigid to beta H about 3. And so you can see it's kind of falling in there. If you take the difference for each individual value of beta H, you can form a residual. So this is the measured minus the predicted. And the important thing here is that the Ostadon results, which were quite different, profoundly different from the centrifuge tests when interpreted with mono Biokabi, are now kind of right in the mix with these tests from Berkeley in blue and the Boulder tests in red. So you're looking for something that is close to zero. There can be dispersion, but you want a lack of a trend here, which the method provides. In the case of mono-Biokabi, if you do exactly the same thing, again, the Ocedon results are significantly underpredicted. All the centrifuge tests are overpredicted, and a substantial number of the centrifuge tests, you can't even formulate a solution because the seismic earth pressure from the method goes to infinity. So I'll summarize. Seismic earth pressures on walls result from relative displacement. They are not related to acceleration in a direct way. These relative displacements can arise from inertial or kinematic mechanisms, and our pseudostatic limit methods do not capture either of those mechanisms. There is no fundamental relationship between these seismic earth pressures and PGA. If we go to SSI-based procedures, we're able to capture the observations from a wide array of sources, and we're able to resolve conflicting findings from the literature. That's what tends to happen when you do things on a fundamental basis. Usually works out that way. We need to have a different type of analysis for inertial and kinematic, just like we do now for the other analyses you've heard about here in this session. And the simplified procedure that I've described is now in a NIHRT Part 3 paper, publicly available, which I think gives some justification for using it. But I think the next step in all of this is we need to start seeing this get used. Inevitably, issues will come up. That's always the case. Maybe we need an ATC project on this topic so that we can advance our practice. These are the papers I mentioned, and the procedures are actually available on a publicly accessible DOI, which you can run in the cloud. And my collaborators, I'll just say this to conclude: Scott Brandenburg at UCLA, George Milanakis at the University of Bristol, Maria Giovanna Durante at the University of Texas, but actually living in Italy. Thank you very much.
Thank you. Thank you very much, Professor Stewart, for this great presentation. So we have just very limited time for questions and answers. I see here one question for Dr. Nikolaou. What is a specific earthquake, between quotation marks, in functional recovery? Is it a signeo-deterministic approach for a scenario earthquake?
Yeah, I saw this question. I think it refers to one slide that I showed that talks about a specified earthquake. So it can be deterministic or probabilistic in the same way that we have different levels of earthquakes in performance-based design, and we have different performance expectations versus having different levels of earthquakes probabilistically or deterministically, and different recovery times. And actually the framework gives some general guidelines or opinions about what these recovery times should be based on RC categories, risk categories per ASC 7 for buildings.
All right, thank you very much, Dr. Nikolaou. I think there is another one here, probably this is for Bret. Do we also consider base slab averaging embedment effects on vertical acceleration response spectrum?
You know, I'm going to pass that to Dr. Stewart, who I think could give you a better informed answer than I could. I mean, in practice, we are only applying that to horizontal motions, but John could do a better job of answering whether there's available research on applying it to vertical spectra as
well. There is an effect on vertical. We don't have sort of procedures that are in our guidelines documents, but just anecdotally, we do see it in the vertical direction. And when I say see it, what I mean is if you look at the data from sites that have an instrumented building and an adjacent ground site, and you simply compare the ground motions from the ground site in the building, there's differences. It's these differences that largely underlie our procedures for the horizontal. There are also differences observed in the vertical. My anecdotal experience, because I haven't sort of assembled this across a large database, is that the reductions are not as great. But we don't have a hard procedure. This is actually something I would like to look at, but we haven't done that yet. But from first principles, anything that's spatially variable in the free field should be reduced as you go into the structure, and that would include the vertical.
Okay, thank you very much, Professor Stewart. And this is the last question. For an existing building, we can determine its fundamental periods by operational model analysis. We can also have measurements from the soil or foundation level to identify its dynamic parameters. Can we have a conclusion on if SSI is important or not by evaluating just vibration records taken from building and soil?
So I could take a stab at that one if you like. That was essentially the subject of my PhD. So the answer is yes, you can do that. You'd use procedures in system identification, and from this, you can see directly the period lengthening that Bret was talking about, the effect on damping, and the ground motion changes. So absolutely, you can see it. And it's a very effective way to provide insights into when it's important and when it's not.
I think there's a couple of different flavors to that question, though. You know, one is if you had records, you know, in an earthquake, say before and after, but let's say that you didn't have earthquake records and you just had vibrational measurements of the building. One of the things that you would have that would be really valuable there is you'd have a very good understanding of the period, at least in ambient shaking, right? So that equation that we were showing, that kind of rule of thumb equation where period was part of it, you'd have a really good period there that you could use in it, and that would help you.
All right, so I think that we are already over time now. So thank you very, very much to the panelists today. Thank you for your presentations. Thank you to our sponsors, and thank you to all of you for your attendance, participation, and continued support. For those who are interested in PDH certificates, please email to eeri@eeri.org. And we are already working on organizing the 4th Kenji Ishihara Colloquium Series on earthquake engineering next year, probably in the spring, here in San Diego. So if you have any topics of interest to be covered or the theme for the colloquium, please let us know. And again, thank you very much.